I have no idea why I'm the lead speaker here, because I'm sitting in a room with a lot of people saying that life is information. I took this from Yvonne's webpage. The second thing is actually from Christoph's webpage. I'm one of these people who thinks that no, life is chemistry. It's not information. Life is a self-sustaining chemical system capable of Darwinian evolution, which means it has information that arranges to copy itself, but the copies are with errors, and what's magical is that the errors are themselves copyable. Now, Sarah Walker, who is not she's not here. Is she here?
That's my understanding, but she's not.
Well, she keeps telling me that we would be doing better, I would be doing better, if I only understood that life is a non-trivial trajectory through phase space. And I have read a dissertation by Cole Mathis, and I noticed that some people are from her lab. There's also this great paper with Lee Cronin where I'm being told that if I just figured out what you guys were talking about, I would be much better at doing what we do. And so that's why I'm here. While I'm giving my talk, well, here's what we do in my lab to try to get the rules of life. So we start with modern life, and we work backwards in time doing evolutionary analysis. You heard a lot about this from Olivier this morning. To go back to more basic, minimal forms of life in the hope of understanding how natural selection evolves proteins and functional molecules. And there's a paper we published in Accounts of Chemical Research a couple years ago on this. We go in the other direction. We start with stuff that you find in atmospheres on a Hadean Earth and get RNA out of it as the first evolving molecular system. So we can tell you that by combining physics and geology and chemistry, life most likely arose in the Darwinian form about 4.36 plus or minus 0.05 billion years ago. And you can read this paper if you would like to understand how we come up with that information and how that happened. Of course, we really think we are trying to understand life by creating our own version of it, because if we really understand what life is, we ought to be able to make some, and that's the synthetic biology approach. I'll have a few words about this today. Of course, we also do a lot of work with NASA, and you can read some of the papers on this as well, where we are trying to find life. We haven't found any extracellular, extraterrestrial alien life yet, but if we do, it will be really quite useful in understanding what the rules are. But at no point in any of these does the word information appear. Now, I'm not here to persuade you that this is better, or for that matter worse, but we really do have to work to manage the chemistry versus information views of the world. And so when you get to Cynthia Collins afterwards, or Arl, or the other people who are going to be talking to you about higher order biomolecular function, right, it's actually a lot of work to get the reality of biology and the reality of biology that is chemistry superimposed upon the mathematical formalism that you derive for it. So, okay, we're talking about analogies, right? Remember, DNA gives RNA, gives protein, actually is a code, right? There's a clear text, there are encoding, decoding algorithms and heuristics. But most of biology really is not a code. Now, you'll see people talk about protein folding as a code, but it's not really a code. Life has information, but in the sense that it is improbable in a meaningful way, then that's an entropy argument. But it's really the only digital information we have is directly involved in evolution. Life is actually mostly information that's transferred back and forth in non-digital forms. And of course, this bioinformation arose by hacking with very strong chemical constraints. And so when I looked up these organizers, I discovered that they agree with me. This is from Max, right, who is talking about how you actually are transferring information not by electric current going down wires, but by diffusion of molecules through three-dimensional solution. And that's a very different problem. And this is a paper actually in IEEE on noise analysis. This is actually from Yvonne's webpage also, right? The DNA sequence of an organism is the result of millions of years of maintenance revision performed by the worst possible set of kludge using spaghetti coding, opportunistic hackers who delight in clever, now I've crossed out the word clever, tricks like writing self-modifying code and relying on undocumented system quirks. And that is actually quite correct. So let me now just try to introduce the theme today of this connection between information and biology by making these points. I won't have time for them all, and I will be stopping as far as I go. But first, you got to understand there's only a few classes of molecules can implement digital Darwinism. They must have a repeating backbone charge, and they must have building blocks that fit into Schrodinger's aperiodic crystal structure. And that's a universal biosignature. You can go study that all over the place, but that's going to be the first point. Only a few classes of molecules can do digital Darwinism. Everything else is analog. The second, that means that formal models that are almost always done by analogy with digital computation generally fail, but they can still be valuable because the difference between how biological molecules as chemicals actually behave during divergent evolution, for example, under functional constraints, versus how the best mathematical formal models for these functional constraints, molecules predicts them to evolve. The difference between actually perform and how the formal models said they should perform actually contains a signal about the function of those molecules in living systems. And that's extremely useful even when the formalism doesn't work. The third is that people talk about evolutionary history as if you can't build a time machine. But the history of analog information is actually directly accessible to you by Jurassic Park experiments where you resurrect ancient dinosaurs, bring them back to life, and see how they behave. And that can be done on a molecule-by-molecule basis. Nobody's done the dinosaurs yet. The next one is that analog information landscapes are extremely rugged. Now, I'm not going to have time to get to this. It would require that I have a long discussion with Olivier, who's actually told you something a little different. But let me skip over that because I want to have time to talk about the final point, which is that information can fix defects in the digital molecules as you've gotten them, okay, by the biological hacking that I just mentioned. So you'll find that when you have to actually transfer information by diffusion through three-dimensional space, not through electrons running down a wire at the speed of light, molecules precipitate, there's off-target binding, there are slow rates that are insuperable problems for information transfer, retrieval, and use, but the chemistry can fix those. All right, so those are the points. Let me go through them stepwise. Let me start with a statement that only a few classes of molecules can implement digital Darwinism. And you have to sort of ask what kinds of biopolymers can do this. And there are two rules I just told you. First place, the building blocks must fit into what's called a Schrödinger aperiodic crystal. And that's going back to a book, What is Life, by Erwin Schrödinger, 1943. He knew nothing about DNA, but he knew that he could not use simple binding to guarantee high information transfer, because binding is a sigmoidal curve, and you have half binding and three-quarters binding, and that's not a good way of maintaining and transferring information of the amount that he realized was necessary for you and me to have children. So, but for that, Schrödinger invoked the physics of phase transitions. And so for that, he's looking, for example, for the organic chemist, the melting of a crystal, a very sharp point, very narrow phase transition, melting of ice, for example, and that's because of a cooperative effect of the physics of phase transitions. And he wants to exploit that for information transfer. And to get that, since ice, right, has the repeating molecules, it contains no information. Because all the water molecules are the same, he wanted to have water molecules that were slightly different but would still fit into the crystal lattice of ice, so that when you melted it, it would still have a sharp phase transition. And that is a way of ensuring fidelity of incorporation. Now, the GACT pairs in DNA are very close to fitting into the aperiodic crystal structure, which is why the melting of a DNA duplex is very sharp. He did not know about this, but when Watson and Crick 10 years later came up with the structures of DNA, and they looked at the structures of GACT base pairs, the first thing that they did not say is, yes, this explains Erwin Schargraf's rules that AT are always present in DNA in the same amounts in GC. No, they said first, this fits Schrödinger's requirement for an aperiodic crystal. Now, I won't talk much more about this. I want to dwell on the other one. The second thing you need is a molecule that keeps its properties constant with changing digital information. And for that, you need a repeating charge in the backbone. And that can be a negative charge, or like it is in your DNA, or it can be a positive charge, like it might be, for example, in the DNA of an alien that we find on Europa. Now, we infer that digital Darwinism needs a repeating backbone charge because we have made many molecules that are analogs of DNA that don't have a repeating backbone charge. And I'm just going to put a couple slides up. This is an empirical statement, okay? It's nothing to do with theory. It's a lot of work, and I won't even spend a moment discussing that work, but it's actually what you might expect Because you've got to remember that Darwinian biopolymers must change their digital information without dramatically changing their physical properties, such as their solubility, or their molecular recognition rules, or their reactivity. So imagine how much more difficult computers would be if when you mutate this binary string, with that red one, into a 0, and now the transistor precipitates or explodes or some property changes, okay? No, the property of the system, the word becoming flesh, as John would say, can't change when you change the information content. And that's actually very difficult to do. Proteins don't do that. Saccharides don't do this. Nylon does not do this. Behavior changes in these polymers very dramatically, even with small changes in digital information. And one of the ways you know that, if you're a biochemist, is you know about sickle cell hemoglobin. 500 amino acids in the protein, very concentrated in the red blood cells. That's important for function. Change one lousy amino acid and the hemoglobin precipitates. And if you don't know that from hemoglobin, you had an egg this morning, which when you took it out of the shell, all the proteins were nicely soluble, but they are metastable with respect to their precipitated form. You put a little heat in it, and what do you get? Precipitated proteins. And so the point about the repeating charge is it prevents that precipitation. It so dominates the properties of DNA that replacing a base, that is the digital part of evolution, changes the physical properties only slightly. And this gives rise to what's called the polyelectrolyte theory of the gene. We published a paper on it about 20 years ago. And the idea here is that, yes, this repeating negative charge controls the interaction between two strands here in this cartoon form. In fact, if you're a student, you think, hey, this is crazy. Why would I have a polyanion, one strand of DNA, binding to another polyanion, another strand? After all, negative charges repel. Well, they do. And that forces the interaction between G and C and T and A to the tippy edges of the bases, as far away from the backbones as possible. And that's actually what gets you the rules. If you make the analogs of these molecules without those negative charges, you don't get Watson-Crick pairing. Right? It's the repulsion here that's very important. And of course, it also allows the biopolymer to change its structure by allowing you to make mutations that will not change the properties of the protein, because changing a G to an A or a G to a C perturbs the molecule a little bit, but the negative charges so dominate the behavior of the molecule. And this is a universal life detection approach, as I mentioned. So that's only a few molecules can do it. We actually can recognize them. They have a and then, by the way, this is in water. If you go to Titan, the largest moon of Saturn, where the oceans are made out of methane, we've tried to make molecules that function as a rule-based molecular recognition system on methane, liquid methane. It doesn't work, but that's partly because methane in its liquid form is so cold. All right, so fair enough, good. That's great. But now, we do have the DNA molecules in your body, which do have a repeating charge in them, and we do try to describe those molecules and their evolution using formal models. You heard a little bit about it this morning from Olivier. And so let me just talk a little bit about this, is because this is actually where biomolecules are the most seductive to the people who do information science, right? Because you look at that, that's the sequence of a part of a protein kinase gene. This is a homologous protein kinase gene from another organism. And you know, why would someone who works with digital information not try to impose their framework on that string? It's obvious. And so bioinformatics, starting in 1960 with Pong and Zuckerkandl, built an increasingly complex formal set of models to describe the evolution of digital information. This was Felsenstein talking about inching towards reality in those models. And so, you know, you can do a simple model where you score identities. Hey, good. Put vertical lines. That is, A here is the same as the A there. A V here is the same as the V there. Great. No chemistry at all. And it turns out that that's not a very powerful way of describing the evolution of those molecules. So what did Margaret Dayhoff do? She added some chemistry to into this Markov model towards reality. Now the Markov model is really quite clear, right? So not all amino acids are different, are the same, right? So Dayhoff will recognize this in a minute, and Olivia has already mentioned these matrices that she developed. But the idea is that the amino acid replacements are independent at each site in that string. That the future replacements at the site are independent of past replacements? Yep. Do I have a question? Oh, you're just stretching. Probability of replacement is uniform at each site. Okay. The empirical parameters derived from the database as a whole tell you what the likelihood of an R matching with a W, right? and that a metric for distance is used, and you've heard some of this morning, the number of amino acid replacements per 100 sites was Dayhoff's PAM metric. And by the way, for those of you who are young, that's something called a book. We used to write information in them, and you can actually page through that and actually see sequences written out by hand, typeset, and all the rest of it. It's a marvelous thing. There she is, by the way, just down the street at the Bureau. So here's a Dayhoff matrix. It's, as you heard this morning, it's 10 times the logarithm of the probability that the index amino acids, so there's one amino acid like arginine, and there's another amino acid down here like tryptophan, right, will be matched in an alignment by reason of common ancestry, divided by the probability they will be matched by random chance. So this is an empirical way to capture the fact that some amino acids are chemically more similar than others, and in principle, the bigger the number, the more likely they are to be matched, and therefore the more chemically similar the amino acids are. Now, I got myself one of my most fun collaborations with Gaston Gonnet, who is famous primarily for MAPLE as a symbolic computation program and organizing the Oxford English Dictionary, to work through the database. This is now 30 years old, where we looked at 10 to the 5th families of proteins which were coming out. And we actually put this into a commercial product, which was actually an evolutionary organized database, which actually ended up getting about $3.5 million in sales. But the first thing that you noticed was non-Markovian behavior everywhere. Every place. So, for example, the probability of amino acid X being replaced by amino acid Y changes as the distance between the sequences changes. It is almost as if future substitutions knew about past substitutions and were either going faster or slower depending on what happened. And so, for example, tryptophan, which for those of you who are in the business know as a W, is replaced by an arginine. That happens frequently early in the divergence of two proteins. That is, it is more likely than average to have another replacement. But these are very different chemistries, and the question is, they're as chemically dissimilar as possible, yet in information evolution, they're very likely early on to replace each other. But once they have, by the way, that site will undergo very, very rapid evolution to get something else. Now, that actually is a wonderful thing. It's explained by the code structure. It turns out that although tryptophan and arginine are very different in terms of their chemistry, their codes are very similar. So the code for tryptophan is UGG. You can make 9 possible changes to make AGG, CGG, and so on. Those are arginines. These are cysteines. A lot of them are stop signs. So at low divergence, the code influences the distribution of point mutations. That's, by the way, trivial, but also the distribution of accepted point mutations. That's actually surprising. And so it is driving, the chemistry is being driven by the structure of the code beneath it. But as soon as you get the change, you then evolve rapidly at that site under functional selection. To get rid of that dissimilarity in the chemical substitution. Well, the formal Markov model fails everywhere. So the relative probability of any pair of amino acids will be paired in alignment depends strongly on the evolutionary distance. The probability of a gap is actually inversely proportional to the length of the gap, raised to the 3/2 power, and that is expectation based on polymer chemistry. Substitution at adjacent positions are strongly correlated. You've got a functional protein, you change something here, it's going to change something there. And actually Harris, I think, mentioned this morning these so-called distant correlated variations, right? If the protein folds, three-dimensional structure, that information is very hard to capture in a formal grammar or anything else in a model, but the two amino acids are near each other, so they change, they correlate. And that's actually kind of useful because, you can go back, here you go, that's that protein kinase sequence I just showed you. And it turns out that if you go back and look closely, you'll discover that at site 87, or this is actually site 108, the modern proteins have an E in some of them. That's a negatively charged amino acid. That E was present in the ancestor of this branch of the family. It was a Q even farther back, and in fact some modern proteins retain the Q. Q is not a charged amino acid, for those of you who are not in the business. So you have a change from a neutral amino acid to a negatively charged amino acid on that branch. And at position 87, you have a neutral amino acid L being changed to a positively charged amino acid down that branch, arriving in the derived sequences, and that indicates that those two sites are close together in the fold. You're looking at compensatory changes. Now, we are actually using ancestral sequences to try to isolate the signal out of the noise. If you look at all the derived sequences and don't look at the ancestral sequences, you lose that. This is not an easily modeled behavior, but it actually was used to predict the anti-parallel anti-parallel beta sheet at the center of protein kinase. And of course, we published that prediction before the structure was solved. We sent it to Sue Taylor, who is the biochemist doing it, and she will still find me at conferences 30 years later and say, hey, that was a wonderful prediction, right? Just by compensatory non-Markovian behavior of the system. And there are lots of other cases we have found. So the model has failed. We have not gotten reality. We're not doing it, but no problem. The formalism is still useful because the difference between how the molecules actually behave and how the formalism expects them to behave is telling us about their chemistry, not their information. That is, their analog information, not their digital information. Is that clear? So cool. So we can go to the next point. So the history of analog information is accessible to you, right? Remember, we can and we actually do infer details of the ancient digital information by Bayesian models where we analyze the derived information. In fact, I just did that for you, right? I told you that that guy has a Q. That's an organism that lived 100 million years ago. I know that not because I've ever gotten the fossil or the mosquito that bit the animal out of amber and sequenced it, but because we're looking at Bayesian models of the derived sequences and inferring the probability of Q at that center and L leucine at that center. But the magic of the ruggedness of the landscapes makes it actually impossible to infer the analog information. That is how that protein behaved. Right? What it bound to, how tightly it bound to it, how it diffused and interacted in a signal transduction pathway. This is what these kinases are doing. But what we can do is use the magic of recombinant DNA technology to bring these extinct proteins back to life, where we synthesize the ancient gene, we express it, we study it, we place it in an ancient context. Now, I'm not going to necessarily, help you out with what Arl's going to talk to you about. I can't resurrect the ancient neurosystem or ancient signaling, or what Allison's going to talk about, ancient biofilms or whatever. I don't know what you're talking about, but I'm just making the assumption. But we can do pieces, and the pieces are kind of amusing. And we can have fun with it. So, for example, when did the digital information evolve to let your ancestor, there you are, you're related to the tarsier and the lemur and to the mouse, when did it let you evolve to drink alcohol? Oh, okay. There's the alcohol enzymes that are digesting alcohol. They oxidize ethanol when you drink it. They're in your esophagus and so on. There's their sequences. And of course, you can see I've highlighted in red places they've changed. We can go back and infer the sequence of the last common ancestor of all these guys, as well as intermediate stages. And this is published in PNS about 5 years ago. And we can put the genes that digest alcohol in a tree, and I can give you some benchmarks. So there's where the dinosaurs go extinct. There's where the old and new world monkeys diverge. This is where you start to walk upright. There's where civilization emerges. And this is in the age of the dinosaurs where ethanol actually first emerges on Earth. And so we can resurrect these, and then we can measure the properties, specifically the ability of these ancient enzymes to digest ethanol. You got to keep in mind that alcohol in chemistry means many things with an OH group on ethanol. It's just one of them. And we can, by resurrecting these, what we'll discover that going way back in time, this thing doesn't have activity with ethanol at all. This guy doesn't have activity of ethanol at all. This doesn't have activity of ethanol at all. It acts on these higher terpenols, as we like to call them, higher molecular weight species, which you're eating back there as you're plucking fruit off the trees. But right here is where you have mutations change. Right when you get up out of the trees, start walking around picking up fermenting fruit that has fallen and it has fermentation, right? Then you have mutations that let your digestive enzymes now metabolize ethanol. And so you can go back and read this. But the point here is that you think you've lost the analog information because you can't really say by looking at a protein what its function is with respect to these two substrates. But you can resurrect them, and you can actually correlate not the molecular properties with the organismic and systems properties of the organism in which those proteins are embedded. By the way, a lot of this is a lot of fun, right? Formal models can be used to talk about, say, the rates of changes in proteins. So this particular tree has the same numbers of B's and M's and A's, and that is, the amino acids are variable at the leaves of the tree in the modern proteins. Here we have just the same, but you'll notice the distribution is different. Here, the rate of evolution is more or less the same across the entire tree. Here, This branch has rapid evolution. This branch has slow evolution. This is called heterotachy. You can read some papers about it. But the bottom line is it means that the amino acid valine at this site in this branch of the tree is under stronger functional constraints than it is in that branch of the tree. Somewhere down this branch, function has changed. Functional constraints have changed. And you can take that, go right back to the alcohol dehydrogenase, and you'll discover that the amino acids in purple are the ones that are changing rapidly in the branches of the proteins in your liver and ancestor that are going to do the, well, you're identifying the mutations that let you drink ethanol. I'm not going to get at this point to the discussion of landscapes, so let me go highlight that as purple and move on to the last, as that chemistry can fix these defects. Now you got to keep in mind that natural DNA is God's mistake, all right? I mean, AT pairs with 2 hydrogen bonds, C pairs with 3. That gives you no ends of problems, right? Polyanions bind to polyanions. Hydrogen bonds are used in water, which is nothing but competing hydrogen bonds. Using flexible molecules, there's major groove binding, there's all sorts of non-canonical binding. But you say, but Leonard Edelman did computation with DNA. Well, that is the biggest examples of beginner's luck I've ever seen, if it was not outright fraud. So, sorry, I didn't say that. But the bottom line is, look, so Microsoft, IARPA, other people want to store/retrieve information in DNA. In 2016, Microsoft, with all of its financial muscle, was to deliver a product to store the Library of Congress in DNA in 3 years. In 2019, this is what they have, okay? And the question is, why do they have it? And the answer is because of differences between transfer of information via diffusion in bulk solution versus by electrons and wires. I mentioned precipitation. We are using polyelectrolytes to get rid of it. I mentioned you're in 3 dimensions, not 1 or 2 dimensions. Everybody likes that for DNA storage, right? Because you get more volume, right? You can store more data. But of course, that means you have to find the information in that volume. The diffusion of a probe is slow. That's a fast 10 to the 6 molar to the -1 second to the -1 is, right? But that means that if you have 1 molar of DNA probes, of 1 million of them, which is roughly solid DNA, the time constant for finding information in that volume is on the order of 1 second, which is the clock speed of your computer, which if you're a useful person, right, doing computation with electrons, right, the clock speeds are nanoseconds or something like this. And of course, the low information density of 4-letter DNA is admittedly not as bad as binary, but it's still not very high, and that's a problem. So think about trying to use hybridization of, say, this strand. I've abbreviated to 5 nucleotides. They're actually longer, to bind to this and then to do polymerase chain reaction to amplify this. Right? That's great until you have a second molecule in the mix which has a different sequence. Say we have got a C here instead of a G here. And now the primer will stick to this, but with a mismatch. Now, the primer it's the wrong place, but it will dwell for a time before it finds the time to release itself after it decides it's in the wrong place and go find the right place. And so how long must a primer be to retrieve 1 molecule from a DNA containing an exabyte of information? Well, it's like 20 nucleotides long. It's got to be long. With just 4 letters, the information density is not so high. And of course, it's going to find close mismatches. It will dwell before it dissociates. And this makes this a big problem. And it's what you do whenever you do PCR. And I don't know how many of you, who does PCR here? Raise your hand if you have done PCR. That's what it looks like, right? Okay. You do a few cycles of PCR. The primer dimers are binding to each other because you have this kind of interaction. Of course, then you have off-target priming. If you're priming in a gut, you get all sorts of off. So for the chemist, this is expected. For the bioinformation scientist, this is bitter betrayal, right? Because they say, oh my God, A is supposed to pair with T and G is supposed to pair with C. And this mess defeats multiplexed analysis. And I just love the guy. I went back and read all of your papers. So here's something from Ivan's lab where you're talking about trying to get this multiplex PCR in cancer therapy because we want to amplify at the same time 100 genes from you to sequence them, to see where the mutations are so we can decide what drug to give you, right? So this is, I'm in trouble now. So let me just say that all of these issues disappear when you had DNA with 6, 8, or 10 letters. That is, in fact, the extra letters in molecular form, but it's easy to just look at these as Lego forms. We have hydrogen bond donors and hydrogen bond acceptors that we have shuffled among those. And this extra letters fit the Schrödinger aperiodic crystal structure. There's our structures. They all have the same size and shape. And they clean up PCR mess enormously because you have higher information density, and so instead of having this kind of a PCR gel, there's a amplification of threefold, three cancer genes actually. They're clean, high yielding, without crosstalk because you've increased the letter information density of it. And from this, by the way, has come $1 billion lifetime sales product, which is why I can run my own nonprofit foundation from getting money from sick people. And so, as my last two slides, let me just give you a little example. We've taken 8 letters out of these to make an 8-letter DNA. The Japanese for 8 is Hachi, so hence Hachi-Moji DNA. So the question is, how much have we increased the information density? So all those who agree with the science news writer says we've doubled it because we've gone from 4 letters to DNA, 8 letters. I have not heard the talk this morning from Thomas, right? We've added 1 bit. We've made 2 bits to 3 bits. But the challenge is now for this system is that it must be able to store information with regular rules. It does. That's the polyelectrolyte backbone. It must be able to transfer the information, which it does, to 8-letter RNA. The receiving system must have a selective phenotype, which it does, and the information must be able to evolve. And in fact, what's kind of fun about this is you can put these systems in the presence here of liver cancer cells or breast cancer cells and evolve molecules out of 8-letter DNA that bind selectively to liver cancer cells, sort of like an antibody, but it's made out of an 8-letter DNA rather than a 4-letter DNA. And of course, these molecules are actually better at binding than the same kinds of molecules that you make out of 4-letter DNA. So for that, let me stop. Those are the points. Only a few classes of molecules can make this bridge between digital information and chemistry. And those have these particular structures, a repeating backbone, uniform sizes. Second, we can have models to describe more complex information, including biological information that's analog in terms of its being read. Those models will generally fail, but that failure is useful because it lets you identify the residual, which is the information that you're interested in biology and chemistry. The history of these of the analog information is accessible to you by inferring ancient digital information and, of course, using laboratory experiments to bring the ancient information in analog form back to life. And chemistry can fix the defects in the natural molecules that you've gotten for digital information to make it more useful to you when you go into the lab. With that, let me stop. Thank you for your attention. And how far over my...
And we've got time for a question while the next speaker comes up and hooks up. So, yeah, maybe in the back.
So thanks for a great talk, Steve. This is Olgica. We chatted just a few weeks ago. So I just want to make a correction, if possible. The PCR-based random access method is a method developed by UAUC, not by Microsoft. And in addition, the team in UAUC has actually developed coding theory methods that will get you away, that will mitigate the problems of primer dimers and of undesired amplification. And it's all due to the use of coding theory, because you have the ability to select the primers you use for random access. So in that context, what would chemistry really improve in terms of what coding theory cannot do? Because selectivity through careful selection of the primers at large Levenshtein distance will get you very precise binding, and it will get you the right amplification and no primer dimers. So that can be provably shown through coding theory.
Yeah, thank you. Yeah, I stand corrected. Don't let me think I suggested that Microsoft invented the PCR recovery of information from POTS. That's not the case. Yeah, keep in mind that we are living in the world of diagnostics, which goes roughly from 100 to 10,000 amplicons. We actually have used informatics to try to minimize primer-dimer formation, and it really does work. Right? It works for about an order of magnitude. But when we get up to tens of thousands, and maybe it's because we're not applying what you guys have done correctly, and for that I'm desperately interested in cornering you, which we've promised to do 2 weeks ago. We have well, I didn't talk to you about the self-avoiding molecular recognition system, which is another kind of DNA which does this separately with the different mechanisms, we're able to get about 10,000-fold amplification of independent sequences with no particular bias for next-generation sequencing. And so, I think it's I don't think it's a competition. I think we can use both. And so, we'll have to talk a great detail about the chemistry that makes the chemistry have certain advantages the informatics does not have, and the informatics has certain advantages that the chemistry does not have.
Great. Thank you very much, Steve. We got to move on. All right, our next speaker will be Dr. Cynthia Collins. Oh, yes, good. Well deserved.